Okay, so in this video I want to consider the family of equilateral triangles which are inscribed to a fixed parabola. Okay, so I can jog through this family of magenta equilaterals and try to study a few features related to their loci. So the first thing that you notice is that the locus of the centroid of these triangles is on a parabola. Okay, I haven't derived. So this blue one here is being drawn as a unit parabola. Okay, so its focus is 1/4, and it's a parabola. If you draw the x-axis along the tangent to the vertex, it's going to be the simple equation of the unit parabola, where y equals x squared, and that's it. So this is y equals x squared with the x-axis tangent to the vertex. Okay, and what I did here behind the scenes is, thanks for Arseny Akopian for giving me a pretty easy method to compute this family. I'm actually drawing the continuous family of equilaterals inscribed to a parabola. Now you think that these two very basic objects in geometry, when put together, would do things that are interesting, and there is a couple of things that we've been able to observe already. One of them is that, in fact, the locus of the centroid of this family of equilaterals is a parabola. So it'd be nice for us to derive geometric information for this parabola. I welcome any of you to do this. What I did here as well, because if you start playing with triangle centers of an equilateral, you're going to get the centroid. So I try to move away from the equilateral, and I'm studying the family of polar triangles of this equilateral with respect to this blue parabola. So the size of the polar will be tangent to the reference parabola at the inscribed vertices of my equilateral. So as I move my equilateral around, I get a family of polar triangles. And what you're seeing here is actually, first of all, the fact that the area of the polar triangle is modulo direction twice, the area of the equilateral is dynamically twice the area of the polar. You can see that I'm showing the areas dynamically up on top, and that ratio doesn't vary. So that's pretty nice. Secondly, you're seeing that, as expected, the circumcenter of the polar contains the focus. Let's turn off this green locus. So I can see here that dynamically the circumcircle of my polar family contains the focus, and this is all to be expected. Okay, this blue parabola is in fact an inscribed parabola to the orange family. Okay. Secondly, we can start playing or analyzing, drawing loci of triangle centers of the polar. So let's go ahead and draw the locus of x1. I'm actually doing behind the scenes here a conic detection, so nothing's actually showing up. So what this means is that this green curve here, which probably shoots off to infinity, is not a conic. If you go for x2, my least squares conic detector is saying this guy here is a conic, likely a parabola. What are the parameters of this parabola? How about the circumcenter? Circumcenter, which is the center of this dashed orange circle, is not sweeping a parabola. It's not sweeping a conic, actually. So is this a quartic? What kind of a curve is that? Now, the first very cool result happens with the orthocenter. The orthocenter is actually sweeping the directrix. Now, when I first saw this, I thought it was a big surprise here, but it's actually true for any polar triangle to a parabola inscribed triangle. So the polar will always have its x4 on the directrix of the reference parabola. So this is well-known information. There's nothing really amazing about this, although to me it actually, in the beginning, I thought it was something cool. But then, as you advance through the other triangle centers, so here's x5, x6, x7, you're looking for, anything else. So you hit x13, and that's the Fermat point. And my detector is saying, oh, x13 is a conic. Now you look at this thing, this definitely looks like a parabola. And it looks like this is the reflected image of my reference parabola with respect to the directrix. So that's actually a pleasing observation. The locus of the Fermat point is the reflected reference parabola about the directrix. Go to x14, you don't get anything special. Let's go to x15. X15 is also conic, also looks like a parabola, but it's not exactly reflected about the directrix. It looks like it has the same kind of scaling as the X13 parabola, but it's reflected about a different point, a different line. All right, then you advance over, I believe the next interesting point is X40. Is that correct? Yes, let's go to X40. Now X40 also yields a straight line, vertical line, just like X4. Here's X4, we saw before. Here's X40. Now, is this obvious? What is X40? That's the circumcenter of the excentral triangle to the polars. Why is the circumcenter of the excentral triangles, why is that sweeping a straight line? Mysterious, perhaps obvious, but it doesn't seem obvious to me. Okay, what else? I think this is it. Let's say we can go all the way up to X99 to see if there's anything interesting. This is Steiner's point, nothing interesting. X100, I'm getting a little bit of polygonalization here because of my sampling. But as you analyze a lot of these higher number triangle centers, you're not gonna see anything really interesting. There's a lot of numerical instability here. So the stars are really X2, which is a parabola. X4, as expected, is on the directrix. X40 is a straight line parallel to the directrix, and then you get X13, which seems to be a reflection of the original parabola about the directrix, and X15, which is also a parabola but reflected about a different line. So much for families of equilateral triangles inscribed to a fixed parabola. See you on the next video.